Hello everyone, we are team 23097 and our project was to develop a multi-use spacecraft platform for future space development. Our project sponsor was NASA and our mentor was Professor Sergei Shakrayev. Before we dive in, let's meet the team.
Hi, my name is Justin Saxon and I'm the team lead and the procurement lead for Oasis.
My name is Ruby Huey and I'm the GNC and Meteorite Protection Lead for Team Oasis.
Okay. Hello, my name is Matt Guare. I am the Propulsion and Mobility Lead, and I'm also focusing on the meteorite protection for this semester.
My name is Jocelyn Mahmoudi. I'm the Systems and Software Lead for Oasis 01.
My name is Nico River, and I'm the Electrical and Power Systems Lead for Oasis. Our project focuses on developing an on-orbit refueling station located at the Earth-Moon First Lagrange point, intending to extend the range of interplanetary spacecraft. The station is designed to carry hydrazine and dinitrogen tetroxide to refuel spacecraft mid-mission. The Oasis station is deployable in a singular launch aboard the NASA SLS rocket and is designed for an operational lifespan of 10 years. Oasis will be powered by dual solar arrays, supplying 10 kilowatts of power for the basic operational needs of the unmanned station. Key mission challenges our team identified was the threat of micrometeorites to the fuel tanks, as well as maintaining propellant pressure and the station attitude control as the tanks are emptied during fuel transfer. To combat these mission threats, we prototyped a micrometeorite protection system, improving upon previous NASA designs, and designed an autonomous smart fuel tank to control propellant pressure and create a constant axial moment of inertia even as fuel levels change. We will next take a closer look at the system requirements for the micrometeorite protection.
The system requirements for the micrometeorite protection system can be broken down into 6 categories. The design shall be able to withstand micrometeorite impacts while remaining durable enough to withstand future impacts. The design shall also be compatible with other systems on the tank while remaining lightweight. Thorough testing of the various designs shall also be done to ensure the layers withstand our protection and durability requirements. When combined, these different requirements will hopefully lead to an effective protection system while minimizing weight, cost, and complexity.
The system architecture for the micrometeorite protection system was composed of a NASA configuration and our own Oasis configuration. The NASA configuration was composed of a front wall, followed by 2 different types of fabric, and then finally a rear wall. While for our design, we had a front wall, a layer of fabric, another wall, another layer of fabric, and then finally a composite rear wall.
Now, to take a more detailed look into these different layers, on the left is our NASA configuration, where the front layer was composed of a 0.08-inch aluminum 6061 alloy, followed by an absorption and reinforcement layer composed of fiberglass and Kevlar. And then finally, a rear layer was 1/4-inch aluminum 6061. For our Oasis configuration, it was very similar, but we used 0.05-inch aluminum for the front wall, followed by 6 layers of fiberglass, and then another reinforcement layer of 0.05-inch aluminum, followed by another 6 layers of fiberglass, and then finally a reinforcement layer composed of a carbon Kevlar weave.
To create our configurations, we utilized basic machining techniques on our metal components, and for our material components, we sewed and grommeted the layers after cutting them to size. The most time-consuming and complex part of the process came from the creation of our carbon Kevlar composite. It was composed of 12 separate layers that were individually saturated with a high-quality epoxy resin. The layers were then stacked together and left to cure for 36 hours inside a vacuum bag, which removed any excess air bubbles present throughout the different layers. After the curing process was complete, we were left with a strong and durable layer that we could add to our protection system. After this was done, we were able to assemble the layers by utilizing threaded rods and a combination of nuts and washers to hold the layers at a desired distance from each other.
The first sample to be shot was our own design. It was shot with 5 7.62 by 39mm bullets at 1900 feet per second and generated a minimal amount of debris. Tracking a piece of debris and measuring the distance it traveled over a certain number of frames allowed us to calculate its velocity. In this case, it was traveling at 12.3 feet per second. Now, looking at the NASA design, you can see a lot more debris is being generated. Part of this could be due to the wood being weaker after having been shot, but it is likely due to higher energy in the bullet after going through the layers. Doing the same analysis on the debris generated gave a particle velocity of 16 feet per second, which is 30% higher than in the Oasis design. This leads to the conclusion that despite the layers not stopping the bullet, the Oasis design was better.
The aftermath of our prototype testing can be seen in these images. We're next going to talk about where we went wrong with our prototype testing.
The main issue with our testing is the type of bullet we decided to use. We decided to use a 7.62 by 39mm full metal jacket round, which was chosen because it has a similar amount of energy to a micrometeorite impact. This is a poor choice, however, because it is designed for penetration and it does not shatter on impact.
For future testing, the use of frangible bullets would have been a better choice as they are designed to shatter upon impact, so this would have more closely emulated what a micrometeorite collision looks like. So testing our samples in this way would have led to the bullets being completely stopped by our various layers and allowed us to examine how our configurations actually worked and allowed for a better comparison of the two designs. Through thorough testing and analysis, we were able to come to 3 different conclusions. Our first conclusion was that the Oasis configuration was 30% more energy effective and 40% more weight effective than the NASA configuration. Our second conclusion was that neither configurations provided sufficient protection against high-velocity rounds that were designed specifically to penetrate through objects. Our third conclusion was that future considerations will take into account the designated uses behind specific types of munitions and more closely try to replicate the types of impacts that micrometeorites have in order to optimize future configurations. The system requirements for the smart tank can be broken down into 6 categories. The use of sensors shall be used to monitor different properties of the fuel, which shall provide guidance for how to move the wall, which reduces fuel sloshing and maintains a constant density. The control system that is developed shall be able to accurately predict the behavior of the fuel inside the tank while minimizing energy consumption. It shall be able to monitor different safety parameters surrounding the tank. When combined, these different requirements should lead to a successful tank design.
The system architecture of the smart tank is as follows. A flow rate sensor sends information about how much water is leaving the tank to a smart algorithm, which can then tell the Arduino how far the wall needs to move. This then tells the stepper motor how long to spin until the moving wall hits that desired distance.
Let's briefly describe the hardware that is associated with our smart fuel tank design. Firstly, it starts with the Arduino Uno R3. We have a stepper motor driver, a flow rate sensor, a NEMA 17 stepper motor, capacitor, power supply, and breadboard. When the motor steps, it suddenly demands a lot of current, which can cause the voltage for the Arduino to drop. The capacitor provides a local reservoir of power that can be used to store and supply energy for this demand spike. The stepper motor driver converts pulse signals from the controller into motor motion to achieve precise positioning. A breadboard is an easy way of prototyping a circuit without having to solder everything together. This will be a brief description of our software through a software block diagram. Like any software development task, all the magic happens within the IDE. This is where the main body of the function is programmed in C++. We then connect our personal computer to the Arduino Uno R3. We firstly define our stepper motor pin numbers, as well as defining the flow rate sensor pin numbers. From there, we set pins as outputs, begin serial communication, we step the motor forward, and then we enter a while loop. In this while loop, the condition is if current pulse is greater than previous pulse. If that's true, we step the motor forward. If that's false, we end the while loop. But within the while loop, we set previous pulse equal to current pulse. On the flow rate sensor side of things, we store a variable called current pulse, and we set the pin as input.
Once construction of the tank was completed, it was time to test the algorithm. To simulate fuel transfer, the tank was filled with water. The simulated propellant flow was controlled by a valve at the bottom of the tank, pressurized by gravity. Upon opening the valve to allow water to flow out of the tank, the flow rate sensor trips, telling the stepper motor to begin rotating. As the motor begins to rotate, the threaded rod mounted to the stepper motor also rotates, allowing an attached plate to be pushed down the tank. The flow rate sensor detects pulses created by magnets attached to turbine blades as liquid flows through the turbine. The time between pulses can then allow for measurement of flow rate magnitude. Based on the flow rate magnitude, the stepper motor is then instructed to increase or decrease rotation speed to match the volumetric change of fluid in the tank, based on a simple conversion between the motor rotation rate and displacement of the pressure barrier within the tank. As can be seen halfway through testing, the valve is closed. Immediately, the flow rate sensor stops sending pulses to our pulse counter, and the Arduino tells the stepper motor to stop spinning. As soon as flow resumes, the stepper motor autonomously begins rotating and the plate continues to move with the water level. Once the tanks have been emptied of propellant, the station allows for refilling using the two-way Rafty valve. For our prototype, once refilling of the tanks commences, the flow rate sensor re-engages. The Arduino then reverses the motor direction, at which point the pressure barrier begins to move up the tank to allow for the new propellant volume. This reversible process greatly increases the lifetime value provided by Oasis to other patron missions.
Through testing the smart tank, we were able to draw three main conclusions. The first conclusion was that while our algorithm proved to be effective, the responsiveness of the pressure barrier could be improved by choosing a higher quality motor. We also found that while the proof of concept works, having greater machine precision would greatly improve the results. The third conclusion we were able to draw was that the addition of temperature and vibration sensors would help increase the capabilities of the tank.
We would like to acknowledge the University of Arizona for their funding support which made this project possible. We also extend our gratitude to the AME Machine Shop for their expertise and for generously allowing us to use their equipment. Special thanks go to Richard Wagner for his assistance in testing our prototype.